Hello, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. Tonight we'll take slow, steady steps through one stubborn rule of nature, the speed of light. We'll see why this number is fixed, why nothing with mass can reach it, and how it quietly ties distance to duration and keeps cause before effect. Settle in, dim the lights, and get cozy. But before you do that, take a moment to like the video and subscribe to the channel. We are so close to reaching our goal of 50 subscribers. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world, and I would like to thank you so much for being here. Light itself is an electromagnetic wave, a self-sustaining ripple where electric and magnetic fields trade energy and keep each other going. It is also a shower of photons, tiny packets that carry energy and momentum without carrying mass. In empty space, those ripples and packets all move at the same top speed. The shock is that this top speed is not just for light, it is the speed built into the structure of space-time. If you could ride a flash from one mirror to another, every honest clock and every honest ruler would agree about the same limit. That is why radio waves, X-rays, and even gravity's own ripples move at that same pace. The limit is not a law that scolds fast things for trying. It is the way distance and duration are tied together. Once you accept one simple rule, that all observers who move smoothly should measure the same light speed, space and time must bend to keep that promise. Distances contract a little for fast travelers. Their clocks tick a little slow compared with the clocks they fly past. Those changes are not visual tricks. Muons, born high in the atmosphere, live longer on the way down than they would at rest, so more reach the ground. Jets carry atomic clocks that disagree with their twins on the desk. After a long flight, satellites high above Earth must run with seconds that are pre-offset to match clocks on the ground, or your map dot would drift. The same bending that saves the rule also draws the speed limit line. Try to push a particle with mass close to light speed, and its kinetic energy shoots upward in a steep curve. Each extra nudge buys you less gain. The math summary of that curve is called the Lorentz factor. You do not need the formula to grasp the point. As the moving object approaches the limit, the factor grows without bound, which means the energy you must pour in grows without bound too. No engine and no battery can pay an infinite bill. The universe is not saying never move fast, it is saying there is a ceiling that mass cannot cross. Photons are the special case. With no rest mass, they live at the ceiling by default. Because signals cannot outrun light, cause comes before effect in a clean way. Every event draws a light cone that marks what it can still affect and what could have affected it. That cone is the fence that keeps paradox out. You cannot tap your friend's shoulder before the nerve signal has time to move. You cannot warn a star before its own light has time to reach it. This limit also sets the scale of what we can see. When you look far away, you look back in time. The sun you see is 8 minutes old. The most distant galaxies are ancient snapshots taken when the universe was young. The speed of light is not a nuisance in that story. It is the camera shutter that turns the sky into a layered archive. Even the way we talk about energy rests on this number. Light with a shorter wavelength carries more energy because more peaks pass you each second. That is why ultraviolet burns and radio does not. Yet all those colors still run at the same pace in the vacuum. The constant speed holds the family together while letting energy change with color. There are places where light moves slower than the top limit. In glass or water, photons are absorbed and re-emitted by the material, so the pulse creeps. That delay does not change the ceiling for information or for a single photon in empty space. The hard limit lives in the vacuum, where the fields move without a medium to tangle them. If you keep one idea from this first walk, let it be this. The speed of light is not just a fast number. It is the stitching in the fabric hold. That stitch and the whole cloth of time, distance, and cause keeps its shape. In the next act, we will use the same stitch to explain why moving clocks slow down and why rulers shrink just enough to keep the promise that every traveller reads the same speed, no matter how hard the wind is in their face. Imagine a simple clock made of light, two mirrors facing each other with a single flash bouncing up and down between them so that one round trip is a tick. If the clock rests on your desk, the flash goes straight up and straight down. Put the same clock on a smooth train gliding past you, and between bounces the clock has slid sideways, so the flash must travel a longer diagonal path. The speed of light does not budge, so a longer path at the same speed means a longer tick. From your viewpoint, the moving clock runs slow. Now swap to the rider's view. On the train, the flash still goes straight up and down, and the clock seems normal. It is your desk clock out the window that appears slow. These two stories do not clash because nature trades space and time to protect the one rule that the speed of light is the same for all steady travellers. If a clock loses ticks when it moves relative to you, distances measured along the motion must also squeeze a little, so that when you compute speeds, you still get the same fixed number. That squeeze is called length contraction, and it only acts along the direction of motion. If you could somehow grab a meter stick flying past at a huge fraction of light speed and freeze it, you would find it shorter nose to tail than an identical stick at rest next to you, though nothing has been damaged. It is geometry doing the bookkeeping. The same geometry also denies us a universal at the same time. Picture a long platform with lightning striking each end. A person standing in the middle on the platform sees both flashes at once. A person sailing by on a fast train reaches the light from the front strike sooner because they are moving toward it, and the light from the rear strike later because they are moving away. Both observers use honest light and honest rulers. They simply slice the four-dimensional scene differently. Simultaneity is not absolute, and that is the hinge that lets the speed of light remain the same for everyone, while clocks and rulers adjust. This is not an optical illusion. Muons born high in the atmosphere by cosmic rays decay quickly at rest, but many reach the ground because their internal clocks are slowed by their rush. Particle accelerators rely on the same fact. Beams live longer and skim closer to light speed because time in their own frame stretches. In the 1970s, physicists flew atomic clocks around the world and compared them with twins that stayed in the lab. The airborne clocks came back modestly out of step, exactly as the theory said. Every second of every day, satellites in the navigation systems above you correct their onboard clocks for both motion and height so that your phone's map does not drift. Even on Earth, you can measure a soft version in a tall building. An atomic clock on the top floor logs a few more ticks per year than its twin on the ground because gravity's pull also bends time, a twist we will unpack later. For now, the simple message is that motion slows clocks and squeezes lengths enough to keep light speed locked. If you want the feel of how steep the effect is, imagine a dial that starts at 0 when you rest and climbs as your speed rises. The dial barely moves for airplanes and rockets. At 90% of light speed, the dial has climbed enough to make time slow by a factor of about 2. As you creep closer to the limit, the dial shoots upward and the energy price for more speed shoots with it. That is why no amount of fuel can push mass through the light barrier, and why particles with no rest mass like photons live at the ceiling. You are not missing hidden gears. This is the world making room for one fixed conversion rate between seconds and meters. We are used to exchanging dollars for euros with a variable rate. Here the rate between time and distance is fixed by light, and so the currency in your pocket, ticks on clocks and marks on rulers, must vary with your motion to keep the exchange honest. When you accept that, the famous paradoxes go quiet. The travelling twin really does age less because their path through space-time bends differently, with periods of acceleration that break the symmetry. The rod that will not fit through a door at rest can, at speed, slip through before anyone can shout, because in the lab frame it is shorter. The lightning that seemed to strike both ends together did so only for the observer who cut the scene that way. None of this changes cause and effect. Light cones still fence off what can influence what, and no one sends a message to yesterday. What changes is our habit of thinking there is one cosmic rhythm and one shared now. There is not. There are many local rhythms, each honest in its own frame, tied together by the single stitch that the speed of light does not blink. Keep that picture in your head, and the rest of relativity follows almost by itself. If the speed of light is the top line on nature's speedometer, the next calm question is, why can't we just push harder? The short answer is that pushing harder buys you less and less speed as you get close to that line, because space and time don't behave like a flat highway. They tilt in a way that saves the light speed rule. Think of speeding up a ship in deep space. At low speeds, each burst of fuel gives a tidy chunk of extra velocity. As the ship gets faster, two things happen together. From your viewpoint, the ship's onboard clock runs slow. Its seconds stretch. At the same time, when you add up energy, you find a steep curve. The kinetic energy needed to close the last fraction toward light speed shoots upward without limit. Physicists wrap both effects in one multiplier, the Lorentz factor, that starts near 1 at walking speed and rockets upward as v approaches c. You don't need the formula to grasp the punchline. As speed nears the limit, the factor heads for infinity, so the energy bill does too. No engine can pay an infinite price, no matter how clever the design, because there is nowhere to dump the waste heat and no tank big enough to store the fuel. Particle accelerators are the most honest demonstration. The LHC pours megawatts into protons, and yet their speed barely creeps beyond 99.999999% of light. What grows is their energy and momentum, not the remaining sliver of speed. Cosmic rays that slam into our atmosphere carry energies far higher than we can make on Earth, and still they never beat the limit. This is why relativistic mass, an old teaching crutch, seem to rise. Modern language keeps the mass fixed and lets energy and momentum tell the story, but the moral is identical. Shoving harder buys you time dilation and energy, not a forbidden velocity. Now fold causality in. If you could leap past light speed, the clean order cause-then effect would fall apart. Relativity's geometry says there are frames in which a faster-than-light message sent forward is received before it's sent, letting you warn your past self not to press send, a direct paradox. That's why all observed forces and fields, electromagnetism, the strong and weak forces, and even gravity's ripples, respect the same limit. Gravitational waves from merging black holes arrived at LIGO exactly at light speed within tight error bars. Radio and gamma flashes from distant events keep pace with each other over billions of years to within tiny margins. Where then do faster-than-light headlines come from? Mostly from mixing up different speeds. In glass or water, light pulses move slower than in vacuum because they keep handing energy to the medium and taking it back. That does not touch the vacuum limit. In some materials, the phase velocity of a wave, how the crests move, can exceed c without carrying information. The signal rides on the group velocity, which stays sub-c when the physics is causal. Cherenkov light, the blue glow in a reactor pool, happens when a charged particle outruns light in water, not light in vacuum. It's the optical version of a sonic boom and still obeys the cosmic limit. Astronomers sometimes map jets from black holes that seem to slide across the sky faster than light. That's a perspective trick when a near sea blob races almost straight at us, so each new flash has less distance to travel than the last. Even quantum entanglement, famous for spooky correlations, does not send usable messages faster than light. You only see the pattern when you compare results later with a slow classical link. There is a hypothetical creature in the math called a tachyon that would always move faster than light if it existed. We have never detected one, and trying to fit such particles into a consistent causal theory turns into a knot of problems. Nature, so far, shows no taste for them. All this might feel like the universe is fussy, but it's the opposite. By fixing a maximum speed, the universe guarantees that different observers can disagree about distances and at the same time, while still agreeing about what can cause what. The speed of light is the conversion rate between seconds and meters that keeps the books consistent. It is also a mercy for engineering. Without a limit, GPS would not have a stable rule to correct satellite clocks. Antennas could not be phased. Electronics could not be designed with known signal delays. Your brain's own wiring would have to cope with arbitrarily fast surprises. Limits are structure. In practice, they give you a safe fence to build inside. So the plain verdict is this: you can go close to the limit and reap useful effects. Time dilation for fast travelers, longer lifetimes for particles in accelerators, tighter beams and higher energies for experiments. But you cannot cross it with mass or messages without tearing up the causal order that lets the world make sense. The energy wall and the causality fence are two faces of the same stitched fabric. Light isn't fast by accident. Its top speed drops out of the rules that govern electric and magnetic fields. In the 1860s, James Clerk Maxwell stitched together everything Faraday and others had learned about how charges and magnets push and pull. His equations said a changing electric field makes a magnetic field, and a changing magnetic field makes an electric field. Put those together, and you get a self-sustaining ripple that can cross empty space without wires, an electromagnetic wave. Better yet, the math predicted that ripple would move at a speed set by how stiff space is to electric and magnetic fields. Call those stiffnesses permittivity and permeability. Combine them and you get a single number for the wave's speed. When Maxwell calculated it, he found it matched the measured speed of light. That was the click. Light is an electromagnetic wave, and its speed is a property of space itself. Today we lock this in by definition. The meter is how far light travels in a precise slice of an atomic tick, so the vacuum value isn't a measurement that might drift. It's the anchor for our ruler. If the vacuum sets the limit, why does light crawl in glass or water? Because in matter, light has to interact with electrons bound in atoms. Those electrons jiggle and re-radiate, delaying the wavefront a hair at each step. The pulse advances, but it advances by a start-stop dance, so the effective speed falls. That slowdown depends on color, wavelength. Blue light is delayed differently than red, which is why prisms spread colors and lenses must be corrected to focus sharp. This is dispersion, and it's the same reason fiber optic networks care about what wavelengths they use and how long the glass path is. Pulses broaden as colors fan out, and engineers fight that with clever glass recipes and signal shaping. None of this touches the cosmic speed limit. The rule, no information faster than light in vacuum, still holds. You can make the phase of a wave crest race ahead or lag behind in odd materials, and you can even rig pulses whose group speed is faster than c, or practically at a crawl, but whenever you track where a brand new feature, the real information, first appears, the signal speed stays at or below the vacuum limit. That's why Cherenkov radiation, the blue glow in a reactor pool, is not a cheat. The charged particle isn't outrunning light in vacuum, it's outrunning light in water, which is slower, and the result is an optical sonic boom. If we step back into empty space, modern physics adds a twist. The vacuum isn't truly empty. Quantum fields seethe with fleeting fluctuations, and in extreme conditions, near neutron stars with crushing magnetic fields, theory says the vacuum itself should act like a very faintly birefringent medium, a subtle twist on polarization, because those fields tug on the fluctuations. For everyday space, those effects are tiny. The vacuum behaves ideal enough that starlight from billions of light years away keeps phase so well we can see interference fringes and razor-sharp airy rings. Gravity is the other place people think light slows. Careful language helps here. In general relativity, mass and energy curve space-time. Light always moves at the local vacuum limit, but the path gets bent and the schedule gets stretched because the geometry is warped. That shows up as gravitational lensing, background galaxies stretched into arcs by a foreground cluster, and as the Shapiro delay, signals skimming a massive body arrive a bit late. Your GPS has to correct for both motion and height because gravity changes the rate of seconds. The radio waves between satellite and phone still fly at light speed locally, but the road is subtly longer in time than a flat map would guess. Put this all together and the picture is clean. Maxwell gave light its identity and tied its speed to properties of space. Materials slow light by making it borrow and return energy to bound charges on the way through. Clever lab tricks can make pulses look odd without letting information beat the vacuum limit. Gravity never slows light in the local sense. It sculpts the route and stretches the clock. And the quantum vacuum, while not truly empty, is so pristine that across most of the universe, light behaves exactly as the simple story says. The limit is not a suggestion. It's the way the world keeps distance and duration in honest proportion. So cause stays ahead of effect, and the sky we see remains a faithful time machine rather than a scrambled mess. If you want proof that the speed of light is not an abstract number but plumbing for daily life, open your phone's map. That blue dot only lands on your street because the system behind it treats light's travel time as sacred and fixes every tiny way real clocks drift from ideal ones. Each GPS satellite, same for Galileo, Beidou, GLONASS, carries ultra-stable atomic clocks and broadcasts a time-stamped code that says, in effect, "This message left me at precisely this moment." Your receiver notes when the code arrives. Because signals cannot outrun light, the difference between sent and received, multiplied by the vacuum speed, gives a range to that satellite. Do the same with several satellites, and you can trilaterate your spot. In practice, you need at least 4 satellites because your phone's clock isn't an atomic clock. Those 4 solve for latitude, longitude, altitude, and your clock's offset all at once. The numbers are not friendly to hand wave. A GPS satellite orbits roughly 20,000 kilometers up, so the radio code spends about 67 milliseconds in flight. If your timing is off by just 1 microsecond, 1 millionth of a second, your range is off by approximately 300 meters. Nanosecond errors become feet. The system therefore lives and dies by time. Relativity is not a footnote here, it is built into the design. Satellite clocks run fast compared with ground clocks because they sit higher in Earth's gravitational field, general relativity, and they run slow because they are moving quickly relative to the ground, special relativity. Add the effects and a free-flying GPS clock would gain about 38 microseconds per day over a good clock on Earth. That sounds tiny, but at light speed it maps to several kilometers per day of position error. Engineers fix this in 2 ways. The satellite clock oscillators are pre-offset on the ground so that once in their orbits they tick at the same rate as clocks on Earth, and the control segment constantly monitors and steers them so their time stays aligned. More relativistic housekeeping hides under the hood, Earth rotates under the satellites, so the system must correct for the Sagnac effect, the few hundred nanoseconds of timing skew you get because signals travel across a spinning frame. The radio waves also do not fly in a perfect vacuum. The ionosphere delays lower frequency parts of the signal. Modern receivers cancel most of that by comparing two frequencies that the satellites broadcast. The troposphere, the lower, wetter air, adds a smaller, weather-dependent delay that models clean up. Then come earthly nuisances: reflections, multipath, off buildings and water, slight errors in the satellite's broadcast orbit, and local radio noise. The result is an error budget that every honest receiver must tame with calibration, geometry, and statistics. None of these fixes would matter if the speed of light were optional. The entire method is timing turned into distance at a fixed conversion rate. Imagine if information could outrun light. A receiver could never know whether a late signal was slow or took a crooked path, and a fast one could arrive before it was sent depending on motion, ripping up the clean order, cause then effect that the math depends on. Instead, the universe is kind. It gives a hard ceiling and says, build within this. So engineers phase their antennas, discipline clocks with satellites and fiber, and solve a four unknowns puzzle a dozen times a second in your pocket. When things go just slightly wrong, the results are visible. Tall buildings and trees push you off a road as echoes confuse ranges. Inside a tunnel, the dot holds where the last clean geometry said you were. Just after touchdown, a plane's GPS position can wander as the receiver reacquires satellites and re-zeroes its clock. New systems steady the picture with more satellites, better clocks, stronger codes, and help from ground beacons and inertial sensors that keep time between fixes. But the core never changes. The map is really a clock. A code leaves a satellite, races at light speed, and lands in your phone. You compare several such arrivals, solve for position and your own time error, and update. Without the speed limit, and without the corrections that flow from it, your blue dot would drift miles every day. With them, it lays quietly on your street, a calm, practical proof that the fastest thing in the universe is also the most useful yardstick we have. If nothing outruns light is more than a slogan, there should be a trail of tests that say the same thing in many different ways, and there is, starting in the 1600s and running through spacecraft and giant lasers today. The first hint was simple astronomy. Ola Rømer watched Jupiter's moon Io slip into eclipse and noticed the timing drifted as Earth moved closer or farther from Jupiter. The only clean explanation was that light needs time to cross space. 2 centuries later, Fizeau chopped a beam with a toothed wheel and measured a round trip to a distant mirror. Foucault swapped the wheel for a spinning mirror and got a sharper number. By the late 1800s, Michelson and Morley tried to catch Earth moving through an ether by looking for tiny speed differences in light, sent east-west versus north-south. They found none. That null result helped push physics to the view we use now. The speed in a vacuum is the same in every direction, and for every steady observer, modern labs keep rechecking with far better gear. Laser beams bounce inside ultra-stable cavities while the whole setup rotates or waits for Earth to turn. If space had a preferred direction, the beat notes would drift. They do not, to parts in 10 to the 17th or better. Particle beams check the same idea differently. When fast ions emit light, the color shift matches the rules that keep light speed constant, and when muons are made to race in storage rings, their lifetimes stretch exactly as they must if the limit is real and tied to time dilation. But that is the lab. What about the sky? The sky agrees. In 1987, a nearby supernova sent a spray of neutrinos that reached underground detectors a few hours before the optical flash. The neutrinos came from deep in the core as it collapsed. The light had to random walk its way out through thick matter, which explains the delay. The key point is that neutrinos and light both crossed 168,000 light-years and arrived almost together. Since neutrinos have a tiny mass, their speed must be just a breath under light speed, which fits the rule. Distant gamma-ray bursts give an even harsher test. If the vacuum made high-energy and low-energy photons travel at slightly different speeds, their arrival times would split after billions of years. Careful watchers find no such split beyond tiny limits, which means C is not color-coded. In 2017, the universe gave us a 2-for-1. 2 neutron stars merged in a galaxy 130 million light-years away, and LIGO caught the rising chirp of gravitational waves, while space telescopes caught a short gamma-ray burst 1.7 seconds later. The delay comes from messy astrophysics at the source, not the trip. Over that distance, the two signals stayed neck and neck, so gravity's waves move at the same speed as light to within parts in a million billion. That is a brutal, beautiful check. Even the ripples of space-time itself obey the same limit. You may remember a headline that neutrinos beat light. That was Opera in 2011. Within months, the team traced the faster-than-light reading to a loose fiber optic cable and a misset clock. When the plumbing was fixed, the odd effect vanished. This is a healthy pattern in science. Extraordinary claims must live through boring fixes before they count. Another common confusion is, doesn't light slow in glass and water? Yes, pulses crawl in matter because they keep handing energy to electrons and taking it back. But the top limit lives in the vacuum. The moment a photon is between atoms, it is back at C. Or can't parts of a wave move faster than C? The crests, phase, can, and pulse shapes group can be made to do strange tricks in special media, but when you track where brand new information first shows up, the signal, it never beats the vacuum limit. Astronomy adds one more sanity check. Images stay sharp. If the vacuum scrambled light speed in a wild, energy-dependent way, distant galaxies would blur. Instead, we see crisp rings and thin interference fringes from sources billions of light-years away, which says the vacuum is an honest highway. Taken together, the story is tight and practical. We define the meter using light speed because it is steady. We test the constancy with lasers that would squeal at the tiniest anisotropy and with beams of particles whose timing is tied to the same geometry. We use the rule to build GPS, which would drift miles a day if the speed limit were even slightly fuzzy. We watch the sky send us mixed messengers, photons, neutrinos, and gravity's waves, and we see them keep pace across cosmic time within tiny error bars. When an experiment seems to break the rule, more careful timing and cleaner cables usually settle it back inside the fence. None of this means the number is magic, it means the number is structure. It is the fixed exchange rate between distance and duration that all honest clocks and rulers must respect, so signals line up in the same order for everyone, and the universe does not let you talk to yesterday. In the next act, we will flip the angle and ask what it means for your own body and ship to chase that limit. How thrust turns into time dilation more than speed, why close-to-sea travel works for particles, and maybe someday for people, and what it would feel like to ride a beam as far as physics allows without breaking the fence. Imagine a ship that can push with steady comfort, about 1 g, so the crew feels normal gravity while the engine hums. On board, life looks ordinary. Coffee sits in cups, you walk down toward the thrust. But from Earth's view, each extra burst of thrust buys less speed than the last, because your time on board stretches compared with home. That stretch is the quiet superpower of near-light travel. Aim at Alpha Centauri, 4.37 light-years away. If you could cruise at 90% of light speed after a ramp-up and then brake at the end, Earth would count roughly 5 years one way, while your clock would tick about half as fast during cruise, so you would age a bit over 2 years in motion plus the ramp phases. With constant 1G flip halfway flight, accelerate for half the distance, rotate the ship, decelerate for the rest. You never sit long at top speed, but you still return younger than people who stayed, because proper time along your path is less. The price isn't romance, it's energy. Kinetic energy climbs along a steep curve as speed nears the limit, so pushing a 1-ton probe to 0.9 C takes on the order of 10 to the 20 joules. Thousands of city years of electricity, before paying to slow down. Again, rockets make this worse because carrying propellant to push propellant multiplies mass. Chemical fuels are a dead end. Fusion only begins to help, and antimatter, while ideal on paper, is far beyond our ability to make or store in practical amounts. That's why serious concepts try to leave the heavy power plant at home and push with light. A giant laser array driving a wafer-thin sail could, in principle, shove gram-scale probes to 20% of light speed, fast enough to cross interstellar space within a lifetime, which is the idea behind Starshot. Tiny cameras on chips, not habitats, surfing a beam without hauling fuel. As speed rises, the sky changes. Aberration squeezes starlight forward into a bright cone. Ahead you see blue-shifted, harsher light. Behind you see reddened dimness, and thin interstellar gas becomes a hazard. Individual atoms hitting your bow at a big fraction of light speed deliver damaging radiation. Dust grains become bullets. Practical shielding looks like layered bumpers that vaporize impacts, sacrificial ice, or magnetic fields to deflect charged particles. But every kilogram of shield is another kilogram to push and keep cool. Heat itself becomes a headache. Dumping gigawatts from a compact ship needs big radiators that glow hot, and hot glowing panels are targets for erosion. By the same fast atoms you're ploughing through. Velocity addition loses its highway intuition too. Fire a drone forward at half light speed from a ship already at half light speed, and Earth won't see the drone at light speed. The relativistic addition rule keeps the sum under the fence automatically, with no paradox. Communication never beats the limit either. Messages crawl at light speed no matter how fast you go, so conversation with home is letter writing with long changing delays. As you recede, your transmissions redshift and slow in arrival rate, and as you approach, they blue shift and speed up. None of this makes the dream pointless. Time dilation is a feature you can use. Beams in accelerators live longer every day because of it, and a crew that solved propulsion, shielding, and heat could cross great distances and return having aged far less than Earth. The sober bottom line is that the fence at light speed is not a wall you crash into. It is a cost curve that climbs toward infinity. Near-light travel is navigation through that curve with clever choices, leaving heavy hardware at home, making ships tiny, accepting one-way probes before people, and with an engineer's respect for a rule that never blinks. The limit holds, always, shaping how skies look, how speeds add, and how clocks compare. Push close to light speed and the universe does not just tick differently, it looks different in ways that feel strange the first time you hear them, but fall out cleanly from the same rules we've been using all along. Start with color. When you rush toward a source, each wave crest has a little less distance to travel than the one before it, so more crests hit you each second. The light shifts to shorter wavelengths, toward blue and ultraviolet of away, and the spacing between arrivals stretches. Colors slide toward red and then infrared. That is the Doppler effect, familiar from a passing siren, but stricter in light because the vacuum speed never budges. Near light speed, the shift becomes dramatic. Stars ahead harden to blue-white glare, stars behind sink into warm red, and finally into darkness. Next comes brightness. At high speed, the sky funnels into your forward view, a headlight effect made from two pieces working together. Aberration compresses directions so that rays from many parts of the sky seem to come from a tighter cone ahead, and time dilation plus Doppler pack more energy into those forward rays. The net is a bright blue cone in front, a dim red wake behind, and a narrowed world at the sides. That is not just a look, it is a safety problem. In the forward cone, not only starlight, but also the thin gas between stars is boosted. Even single atoms become high-energy bullets, and dust grains strike with the punch of tiny shells, which is why any serious fast craft needs shielding and filters just to protect sensors and eyes from the hard glare and the steady sandblasting of space. The last piece is shape, and this one fights your intuition. We say fast objects contract along the direction of motion, and for measured lengths with synchronized clocks, that is true. But a camera is not a synchronized ruler. It collects photons that left different parts of the object at different times. When a fast sphere or box slides by, light from its trailing edge left earlier than light from its leading edge, so by the time the photons reach you, the rear has had time to catch up in angle. The result is that a speeding object does not simply look squashed, it looks partly rotated, as if it had turned to show more of its side. This viewing effect, often called Terrell rotation, does not undo real contraction in measurements. It just means your eyes and cameras are always looking at a stitched-together past. The same logic makes moving patterns bend in odd ways. A checkerboard painted on a fast train seems skewed. A fast rod aimed to hit a target looks offset because the front and back you see are not from the same instant in any single frame. Even the night sky itself warps. Constellations crowd forward. The Milky Way band tightens into the headlight cone, and behind you the star field thins out. If you opened a shutter for a long exposure, the forward stars would trace sharper, brighter arcs than the ones at your side. If you used a fast shutter, faint stars behind might vanish entirely. None of this breaks the fence we have built. The speed limit is still the limit. These are the honest consequences of mixing light's finite travel time with the rule that different observers slice space-time differently. The take-home is simple enough to carry. Near the limit, color tells you your motion, brightness tells you your heading, and shape tells you that seeing is always late. A traveler does not just move through space faster. The traveler sees a different sky because light needs time to get in the door, and the door is closing fast. On roads, we add speeds like simple numbers. A car going 60 passes a ball, thrown 20, and you expect 80. Near light speed, that arithmetic breaks, and the reason is not a trick, but the same stitch we've been using all along. To get a speed, you must divide a distance by a time, and different observers do not agree on the same distance in the same time once their clocks and rulers tilt relative to each other. That tilt, relativity of simultaneity, is what saves the limit. Picture a sleek ship flying past at 60% of light speed, 0.6 c, and a drone launched forward from the ship at 60% of light speed relative to the ship. Highway math says 1.2 c. Space-time math says not a chance. When you do it properly, the combined speed from Earth's view is about 0.88 c, still safely under the fence. Push the ingredients harder, and the rule gets stricter. Any two sublight speeds combine to another sublight speed, and if either ingredient is exactly light speed, the result is still exactly light speed. This is why a flashlight on a rushing train does not blast light faster than light down the track. The rider measures c because light is c in every steady frame. The person on the ground measures c because their way of slicing the scene, how they sync clocks at different places, changes just enough to keep the same answer. That is the universe enforcing one exchange rate between meters and seconds. It also explains why tailwind tricks fail for information. You can sit at 0.9 c and fire a radio pulse forward. Earth still sees that pulse at c, not at 1.9 c. You can stack 1,000 moving stages. The sum remains under the ceiling by exactly the amount needed to protect cause before effect. This is the clean fix behind several famous confusions. A laser spot sweeping across a distant moon can skate faster than light. So can the intersection point of two scissors blades, or the shadow of a bird on a cloud bank. Those are patterns, not packets. No atom, charge, or bit rides with the spot, so no message beats c. In deep space, jets from black holes sometimes seem to crawl sideways faster than light. The blobs are racing at almost c, almost straight at us, so each new flash has a shorter distance to travel than the last, and the apparent motion across the sky is a perspective illusion. The math that keeps the ceiling safe is the same math that stretches time and squeezes lengths. If you insist on a formula, it's a tidy fraction where the numerator tries to add speeds and the denominator quietly cancels the overreach with a factor built from their product and c. But you don't need symbols to carry the punchline. The rule is automatic and exact, and it comes from how space-time mixes space with time for moving observers. Think in energy terms and you meet the same guardrail. Energy and momentum don't add as plain scalars either. They form a four-part bundle tied together by c that ensures massive objects always stay under the limit and massless things always ride the limit. That bundle explains everyday accelerator law. When particles already near c get extra push, their speed hardly changes while their energy and momentum soar, and when two fast beams collide, the shared center of mass frame, the natural rest of the collision, is found by this same careful addition, not by naive road math. Even at human scales, the rule leaves fingerprints. Velocity addition tells you exactly how much headlight squeezing and Doppler hardening you'll see when you bolt the camera to a fast craft, and it's the reason communication with home never becomes real time just because you are moving fast. Your outbound signals still crawl at c in every frame. Your inbound mail still took light years to cross light years. Only the rate your own time passes changes. Wrap it all up, and the message is spare and sturdy. Speeds don't stack the way your gut expects because the ingredients, distance and duration, are not absolute. The same geometry that slows moving clocks and shortens moving rulers also rewrites plus into a safer kind of plus, one that guarantees no chain of boosts, tricks or alignments ever breaks the speed of light. Limits can feel like handcuffs. Here the limit is a hinge. It lets everyone keep honest books for cause and effect, even when they disagree about what is at the same time. And it gives engineers and navigators a reliable rule to build by, from particle rings to probes to the calm math that will carry us through the rest of this night. When people quote E equals mc squared, it can sound like a slogan. It's really a conversion rule that falls straight out of the same geometry that fixes the speed of light. Energy is the bookkeeper for change, momentum is the bookkeeper for motion, and mass is the built-in energy. A thing has even when it sits still. The constant c is the stitch between space and time. Square it, and you get the exchange rate that turns kilograms into joules. 1 kilogram at rest holds about 90 quadrillion joules of energy, not because there's a hidden battery in the metal, but because in relativity, mass and energy are two faces of one account. You see that account move every time the sun shines. In the core, light atoms fuse into heavier ones, and the final ash weighs a touch less than the ingredients. The missing mass shows up as light and neutrinos flying outward, and the sun's total mass slowly drops as it pays that bill. The scale is huge yet measured. The sun loses millions of tons each second, and no one panics because the sun is so massive. The change is tiny over human time. Power plants and bombs are the same story at a smaller tempo. In fission, a heavy nucleus splits, and the pieces plus their flying bits weigh less together than you started with. The difference is the released energy and heat. In fusion, light nuclei bind, and the bound result sits in a slightly deeper energy well. Mass defect is just the new binding energy written in mass units. Chemical reactions do this too, but the mass change is billions of times smaller, so we only notice the heat, not the weight shift. Even a wound-up spring weighs more by a dusting because stored energy adds to the mass account. It's too small to weigh with a bathroom scale, but it's there in the math and in ultra-precise experiments. Photons add a twist that scares textbooks into symbols. Light has no rest mass, yet it carries energy and momentum. How? Because momentum doesn't need rest mass, it needs energy moving through space. For light, the link is simple. More energy means more punch, which is why blue light has more shove than red. That shove is real enough to sail on. Sunlight pushing on a big, thin mirror produces gentle, steady thrust with no fuel burned on board. Laser sails exploit the same trick with an artificial star at home, which is why fast probes are more plausible than fast starliners. The reason these sails work is the same reason satellites must account for sunlight pressure and even the shine from Earth. Light is not a ghost, it's a courier with momentum. Rocket talk often hides the same lesson. Exhaust energy adds to a ship's energy account and gives it momentum. If you could throw pure light out the back, you'd have a perfect photon rocket, miserably inefficient in practice, but conceptually clean. Old rockets trade between exhaust speed and propellant mass, and relativity just keeps the ledger honest as speeds rise. Mass energy also shows up in gravity's language. In Einstein's picture, space-time curves in response to energy and momentum, not just rest mass. That's why light bends near the sun, and why a hot box of gas gravitates a hair more than a cold one with the same number of particles. Heat is energy. Energy gravitates. The fabric doesn't care which pocket it sits in. This is not wordplay. It's what the equations demand and what observations confirm when we watch starlight arc around galaxies. The cleanest way to carry all this is to retire the idea of mass increasing with speed. What increases is energy and momentum. The rest, mass, stays put. As you push a particle near the limit, most of what you add goes into the energy account, not into more speed, and that's the energy wall we met earlier. E equals mc squared is the quiet line connecting every piece of the story. The sun's glow, the heat from fission and fusion, the faint shove on a sail, the way hot matter curves space a touch more than cold. It isn't a magic trick or a door to free energy. It is a translation table written in the same ink as the speed limit, telling you that matter is a way energy can sit still, light is a way energy can run, and c squared is the fixed rate that lets the books balance. When people look for loopholes in the speed limit, the same suspects appear. Optical pulses that seem to sprint ahead, quantum entanglement that links far-flung particles, and the electric blue Cherenkov glow where charges outrun light in water. The plain answer is that nature draws the line at the speed of usable information, the first causal nudge that can change a receiver, and that front speed never beats the vacuum limit with waves. A signal is built from many pure tones. In some materials, those tones add up, so the group velocity, the motion of a pulse peak, can exceed c or even turn negative. That sounds wild, but it only slides the shape of a pulse that the detector already expected. The earliest brand new feature, the front, still arrives no sooner than C would allow. That is the old Sommerfeld-Brillouin result in modern clothes. Dispersive media can shuffle energy within a packet, but they cannot make a fresh surprise show up early. Cherenkov light is no cheat either. A charged particle can outrun light in water because water slows light by constant start-stop interactions with electrons. The same particle cannot outrun light in vacuum. The blue cone is an optical sonic boom, not a note from the future. Now entanglement. Quantum pairs can be prepared so that measuring one lets you predict what you will later read on the other. Even across cities, the correlations are real and dramatic, but they do not carry controllable messages. Your single outcome is random until you compare notes through an ordinary, slower-than-light link. You cannot dial your setting here to write a chosen bit over there. That is the no signaling rule baked into the math. Even quantum teleportation obeys it. The recipe explicitly needs a classical message to finish the reconstruction at the far end, and that message cannot beat C. Field theory says the same thing in stricter language. Operations performed at space-like separation commute, which is a compact way of saying, do anything you want here. There is no measurable effect there unless light could have gotten there. Gravity follows the same discipline. In 2017, two neutron stars merged, and we caught the gravitational wave chirp and the gamma-ray flash from the same event. After a 130 million year race, they arrived within seconds. The tiny lag was made at the messy source, not on the road. Over the trip, the two signals kept pace to within parts in a million billion. If the vacuum made high-energy and low-energy photons cruise at different limits, sharp distant images would smear and light curves would stretch in energy-dependent ways. Instead, we see razor-thin interference fringes and neat stretches that match cosmic expansion, not vacuum slop. People still try clever workarounds, sweeping a laser spot across a far wall faster than C, sliding the intersection of scissors blades, or mapping a near C jet that appears to crawl sideways superluminally because it points almost straight at us. In every case, what moves faster than C is a pattern, not a particle or a new bit, so there is no message hidden in the mirage. Even packing more symbols into one photon does not help. Channel capacity still depends on energy, bandwidth, and noise, and the first detectable change rides the front, which honors the fence. The moral is not pedantry, it is the backbone of a sane world. The single hard limit lets observers who disagree about distances and at the same time still agree about what can cause what. Engineers lean on this every day. GPS converts light time into distance because the conversion rate is fixed. Networks schedule around latency because packets cannot arrive before they are sent, and astronomers trust that mixed messengers keep pace across the deep. Many speeds will dance through the next acts: phase, group, pattern, apparent, but only one matters for choices and causation. The front speed in empty space that one is the fence, and so far every experiment, from tabletop optics to colliding stars, has found it exactly where the rule says it is. If you want one picture that ties all our rules together, moving clocks slow, rulers shrink, speeds don't simply add, nothing passes the limit, it is the idea of the space-time interval, the one measurement that every steady traveller agrees on even when they disagree about distances and times separately. Think of events as dots on a four-dimensional map, 3 for where, 1 for when. Between any two dots you can form a special distance that mixes space and time using the speed of light as the conversion rate. In plain words, you multiply the time gap by c to turn seconds into meters, then compare that time distance to the ordinary space gap. The combined result is the interval. Different observers moving smoothly will argue about how much of the gap was space and how much was time, because their clocks and rulers are tilted relative to each other, but they all get the same interval. That one shared number is the deep reason physics stays consistent for everyone. Slice the map, and three cases appear. If the time part wins, if c times time gap is larger than the space gap, the interval is called time-like. Then there exists a path where one event can cause the other, and the amount of personal time that could pass along the best such path is the proper time, what your own wristwatch would tick if you travelled between those events. That is the real content of moving clocks slow. When you rush and turn and brake, you do not trace the longest proper time route through space-time. You take a bent path that yields fewer ticks than the stay-at-home path. The famous twin story is just geometry. World line. A is straighter, more proper time. World line B is kinked, less proper time. No paradox, only path length in a new kind of distance. If the space part wins, if the separation is too great for light to bridge given the time gap, the interval is space-like. Then there is no way for anyone for the first event to influence the second without breaking the fence. Different observers will disagree about which came first, but that order has no causal bite. Finally, if the time and space parts exactly balance, the interval is light-like. That boundary is the light cone, the set of places a flash can just reach, future cone, and the places from which a flash could just have come, past cone. Light's world lines live on that skin, and because the interval there is zero, every steady observer must assign the same speed to that flash. You can now see why the speed limit is structural, not a scolding sign. If a material object tried to live on the light cone skin, its proper time between events would drop towards zero. That's what our infinite energy wall really means. It takes unbounded energy to squash your world line so hard that your personal time vanishes between two separated events. The same geometry explains velocity addition. When you change frames, you are rotating and rescaling axes in space-time so that your own time axis points along your motion. Those shears mix the space and time parts, changing measured speeds, but because the interval stays fixed, sums that would overshoot c in road math are quietly pulled back under the ceiling. Even the odd Terrell rotation look of fast objects is a shadow of this. What you see is light reaching you along light-like paths from different parts of the moving thing, stitched by the cone. Gravity folds this flat picture without tearing the ruler. In general relativity, mass-energy curves the map so straight lines, the do-nothing paths, become geodesics that bend. Light still travels on light-like paths whose interval is zero. But those paths arc around masses and take longer in clock time than a flat guess would allow. That is gravitational lensing and the Shapiro delay. Clocks higher in a gravitational field tick faster because the geometry gives them more proper time between the same bookend events. Locally, though, in a tiny lab falling freely, the rules reduce to the flat ones, and the limit is the same CE. That is why we say the speed of light is locally constant even in a curved universe. It is baked into the ruler itself. Once you carry this ruler in your head, scattered facts line up. Time dilation is not magic. It is shorter proper time along a bent path. Length contraction is not crushing. It is how different tilts slice the same interval. No global now exists because different tilts carve different sets of simultaneous events through the same stack of dots. And c is not merely a large speed. It is the conversion factor that makes the interval an invariant, the yardstick that never changes even when every clock and ruler does. Before Einstein ever wrote down his equations, the the story of light speed was already one of stubborn patience. Ancient philosophers guessed it was either instant or very fast, but for 2,000 years, no one could prove it. The first real hint came in the 1670s from the Danish astronomer Ole Rømer, who studied the eclipses of Jupiter's moon Io. He noticed that when Earth was closer to Jupiter, Io's eclipses appeared sooner than expected, and when Earth was farther, they lagged behind. The pattern fit perfectly if light took time to cross the widening gap, about 22 minutes for the full diameter of Earth's orbit. From that delay, Rømer deduced light speed at roughly 220,000 kilometers per second. That was low by modern standards, but groundbreaking. Light moved fast, yet not infinitely fast. A century later, James Bradley refined the idea by measuring how starlight appeared to tilt as Earth moved around the Sun, a phenomenon called aberration. The tilt came from the same reason raindrops hit your face at an angle when you walk. You're moving through the falling light. From that simple geometry, Bradley's value for C landed near 301,000 kilometers per second, astonishingly close to today's 299,792 kilometers per second. Then, in the 19th century, the experiments turned from the sky to the lab. Armand Fizeau built a toothed wheel that chopped a light beam, bounced it off a distant mirror, and measured whether the returning flash was blocked or passed through the next gap. By counting teeth and timing rotation, he got 313,000 kilometers per second. Léon Foucault soon replaced the wheel with a spinning mirror and tightened the precision. Every tweak confirmed the same truth. The number didn't depend on color, brightness, or direction. It seemed universal. Then came James Clerk Maxwell, who showed through pure math that electric and magnetic fields could dance together, each generating the other, and that the wave's natural speed in vacuum, derived from the basic constants of those fields, was the measured speed of light. That realization unified optics and electromagnetism into one theory and gave the number new meaning, not a property of photons, but of the vacuum itself. Yet there was still one riddle. If light were a wave, through what medium did it ripple? Sound needs air. Ocean waves need water. What was the ether for light? In the late 1800s, Albert Michelson and Edward Morley set out to detect Earth's motion through this invisible ether by comparing light speeds in perpendicular directions. The result was null. No difference, no ether wind, no frame of reference against which to measure motion. Light speed was the same whichever way Earth moved. This result shook physics. Either every experiment had conspired to fail, or nature itself did not care about our motion. Einstein, in 1905, chose the simpler idea. The laws of physics, and therefore the speed of light, are identical in all steady frames. You don't need an ether because the structure of space-time itself does the job. From there, the tangled facts of contraction, dilation, and velocity addition fell neatly into place. The constancy of C was not a quirk, it was the foundation. Later measurements only hardened that conclusion. Modern labs bounce lasers between mirrors a few meters apart and time the flight with atomic clocks, getting 299,792.458 kilometers per second. In 1983, the meter itself was redefined to lock that value in. The meter is the distance light travels in 1 divided by 299,792.458 of a second. Now, the speed of light is not a number we measure. It's a number we use to define distance. Every GPS fix, every fiber optic pulse, every radio signal between planets carries this heritage. And the truly quiet fact is this: whether it crosses empty space, glass, gas, or the curved geometry around a black hole, the light you see tonight obeys the same invariant rate. The universe may twist, stretch, or bend time, but c stays exactly what it has always been, the rule that measures everything else. Gravity does not tug on light the way a hand pulls a rope. It reshapes the stage so the straightest possible paths curve, and light, which always follows those straightest routes in space-time, appears bent to us while still moving at full speed locally. Picture a beam skimming a massive body. In flat space, it would be a perfect line, but near mass, the geometry dips like a valley. The beam tracks that dip, and its path arcs, which is why stars seen next to the sun during an eclipse appear a little shifted from their true position. Scale that up, and the sky is full of quiet mirages. A single distant galaxy can be split into multiple images by a heavy foreground galaxy. A neat alignment makes an Einstein ring, a near circle of light that tells you mass lies in the middle even if most of that mass is dark. Whole clusters of galaxies work like giant glass lenses, stretching background spirals into arcs and subtly magnifying faint smudges into view. Unlike glass, gravity's lens is almost colorblind. To first order, it bends red and blue by the same angle, because it is the shape of space-time that matters, not how electrons in a material dance. The bend is only half the story. Curved geometry also stretches schedules. A signal that passes deep through a gravitational well takes longer than it would on a flat map, both because its route is bent and because clocks tick differently along the way. Radio pulses that graze the sun arrive a little late, a clean effect called the Shapiro delay. Your GPS quietly corrects for the same principle every second, because satellite clocks higher in Earth's field tick faster than ground clocks, and the radio code between them runs across a slightly longer road in time than Euclid would have you believe light also changes color with height in a gravitational field. Climb a photon out of a well, and it is redshifted, its crests arriving farther apart to a faraway clock. Let it fall, and it is blue shifted, picking up energy as measured by a lower clock, even though along every tiny step it always moved at c. This is not friction or fatigue, it is the bookkeeping of energy when time itself runs at different rates from place to place. Near compact monsters, the effects turn dramatic. Around a non-spinning black hole there is a special orbit where light can circle once or twice before escaping, the photon sphere, a razor-thin ring that helps make the bright donut in black hole pictures closer still. The event horizon marks the place where all future light paths tilt inward. To a distant watcher, flashes from the edge seem to slow, redden, and fade, while an infaller's own clock stays honest and crosses in finite time. Strong lenses add a bonus for cosmology. Different images of the same flickering quasar take different routes and arrive with time delays tied to both the mass of the lens and the overall expansion history. So by timing those echoes, you can weigh the lens and probe how the universe has grown. Weak lensing, a softer, statistical shearing of millions of galaxies, maps the invisible matter that threads space into a web. Through all of this, the fence we've built never moves. Locally, in a small, freely falling lab, light still zips by at c, and the laws look flat. Globally, the stage is curved, so rays bend, schedules stretch, and colors shift. That is the right way to hold the idea. Gravity is geometry. Lensing is straight lines on a curved map. Delays are the cost of running over dips in time, and redshift is what you see when clocks at two heights do not agree. Point a perfect telescope into a clear, dark patch of sky, and you do not see the universe now. You see a stack of yesterdays. Because light needs time to travel, and the speed of light is the fixed exchange rate between distance and duration. That single rule carves three helpful boundaries in our heads. First is the particle horizon, the farthest place whose light has had time to reach us since the hot beginning. Our universe is about 13.8 billion years old, but because space has been stretching while light was in flight, the stuff we can see today sits much farther away now than 13.8 billion light years. Think several times that nothing beyond that horizon is visible yet, not because there is a wall, but because there has not been enough time for a signal to cross. A second is the event horizon of cosmology, the set of places that will never send us a signal, no matter how long we wait, because cosmic expansion is speeding up. Distant galaxies ride the expansion like dots on a rubber sheet we are stretching. Beyond some distance, the sheet stretching carries them away so fast that light they emit today can never fight back to us. This does not break relativity. No object is outrunning light through space. The space between us is increasing, and general relativity allows recession faster than CE without messages hopping the gap. Third is the Hubble horizon, a rough, time-dependent distance where recession speed equals c at this moment. It is a useful scale, not a hard boundary. These horizons explain several quiet facts about the sky. When we watch a supernova in a far galaxy, its brightening and fading looks stretched by a factor of 1 plus z, the same factor that reddens its color. The whole movie runs in slow motion because the light's crests were stretched by expansion. The cosmic microwave background, the oldest light we can see, comes from the moment the hot plasma first cooled enough to let light stream freely. Before that, the universe was foggy and photons bounced around. After that, the fog cleared in a flash and we got a baby picture. That glow is not edge radiation. It is a last scattering surface wrapped around us, the farthest light a present-day eye can receive from every direction. Horizons also set the stakes for one of cosmology's neatest stories, the horizon problem. The microwave background is almost the same temperature across the sky to 1 part in 100,000, even between patches so far apart that, without new ideas, no light could have crossed between them to even things out. The leading fix is inflation, a very early burst of rapid expansion that blew up a tiny, already uniform patch to cosmic size. Regions that look disconnected today were neighbors before inflation and had time to come to the same temperature. Then the stretch locked that sameness in and planted tiny quantum ripples that later grew into galaxies. Whether or not you memorize those names, the practical picture is simple. Because the speed of light is finite and non-negotiable, the night sky is a time machine with a reach set by age and by how the fabric has stretched. There is no center to this view. Every observer anywhere would build their own bubble of the visible, edged by the same rules. The bubble grows as time passes. Light from nearer than the edge places keeps arriving, and very distant, once invisible regions can drift into view if they sit inside the event horizon. But parts of the universe will always remain beyond contact if accelerated expansion holds. None of this changes local physics. In laboratories and solar systems, light still races at sea, and cause still stays inside light cones. Horizons are large-scale bookkeeping that tell us which dots on the grand map can ever trade signals. Carry that, and the cosmos becomes easier to read. Every faint smear in a deep field is a memory. Every redshift is a clock. And the edge of the observable is not a wall but a timestamp written by the fastest thing in the universe. It sounds like a contradiction the first time you hear it. Astronomers say nothing outruns light, yet also say that very distant galaxies recede from us faster than light. The fix is simple once you separate two ideas that our language mashes together. Relativity's speed limit applies to motion through space, the kind of motion you'd measure with a ruler and a clock in one region. Cosmic expansion is not that. It is a slow change of the scale you use to measure far apart distances. Picture dots on a stretchy rubber band. No dot slides past its neighbor, so locally, every dot is at rest. Yet as the band stretches, two far dots get farther apart, and if you divide that new distance by the tick of your watch, you can get a number bigger than light speed without any dot breaking the local limit. That is Hubble's law in plain clothes. Recession speed equals Hubble's constant times distance. Close by, the product is small. Far away, the product can exceed the speed of light, and nothing illegal happens because no galaxy is speeding through its space. The map itself is rescaling underneath them. This is why we talk about two different kinds of horizons. The particle horizon marks how far light has had time to reach us since the hot, dense beginning. Everything inside that sphere has had a chance to send us at least one photon by now. Everything beyond it has not, because there has not been enough time yet. The cosmic event horizon is stricter. It marks the farthest places from which light sent today will ever reach us in the future if the current accelerated expansion keeps going. These horizons are not walls in space, they are boundaries set by time and by how the scale factor grows. Light always moves at sea locally, but the riverbed it swims in is stretching, so some swims never finish. This also explains a phrase that often confuses people. We see galaxies that are now more than 46 billion light-years away, even though the universe is 13.8 billion years old. The trick is that light-year is a distance unit, not a promise about age. While the light was on the way, the scale grew, so the present-day separation of the source can be much larger than the number of years the photon travelled. Nothing about that asks a photon to beat its speed. It also clarifies what inflation did in the very early universe. During that brief burst, the scale factor grew extremely fast, so regions that were once close enough to share the same conditions were flung far apart. People say space expanded faster than light, but again, no object surfed past a neighbor locally at superluminal speed. The scale changed. The local limit stayed. Observations back this picture in several quiet ways. Light curves from very distant supernovas are stretched by a factor of 1 plus the redshift, which shows time itself ran slower for that distant movie because of expansion. The cosmic microwave background is a nearly uniform afterglow with tiny ripples whose pattern matches a universe that has been expanding and cooling for billions of years. Large-scale maps of galaxies show a web that grew from those ripples under gravity, exactly what you expect if space stretches while matter clumps. So the rule set is tidy. Locally, all motion is fenced by the speed of light. Your rocket, your radio, and your particles in a lab all obey the same limit. Globally, the yardstick between faraway points slowly changes, so recession speeds can exceed c without any signal outrunning a light beam next door. Horizons are not cheating. They are geometry's way of telling you which stories can reach you in a finite time. Far from making relativity fragile, cosmic expansion shows how robust it is. The same constant c converts time into distance in the equations that build the map, and that constant stays put even when the map itself grows. The speed of light doesn't just rule galaxies and particle beams, it quietly shapes phones, planes, finance, and space missions by setting an absolute floor under latency, the time it takes a message to matter somewhere else. Even on Earth, most signals ride glass, not vacuum. Inside optical fiber, light slogs along at roughly 2/3 of its vacuum speed because it's constantly nudging electrons in the glass and being re-emitted. That built-in slowdown makes a clean, stubborn limit. A straight shot around half the planet in fiber can't beat on the order of 100 milliseconds one way, and real routes are longer and kinked, so typical coast-to-coast trips add tens of milliseconds on top. Engineers fight for crumbs. They pick straighter paths, bury low-latency cables with special glass, or even hop to microwave links in air because radio in air is faster than light in fiber. and you can draw straighter lines than seabed routes. High-frequency traders literally built chains of line-of-sight dishes from Chicago to New York to shave a few milliseconds, not because of software genius, but because air is closer to vacuum than glass satellites' trade path for speed. Signals to geostationary orbit climb 35,786 kilometers up and back, so even at light speed, that round trip costs about a quarter of a second before you count switching and queues. That's why satellite calls have the tiny, awkward pause. Low Earth orbit constellations promise shorter hops and clever crosslinks, so some long routes may beat fiber by taking fewer, straighter legs through thin air and vacuum. Still, no relay chain outruns C, and every dish, switch and codec adds its own grains of delay. Software tries to hide the physics with prediction, and smoothing video chats buffer. Games guess where your avatar will be and fix it later. Streaming sites prefetch. Error correction resends lost chunks. Those tricks tame jitter but not the flaw. If a friend sits 10,000 kilometers away, best case you feel tens of milliseconds of delay because nature set the exchange rate between meters and seconds and glass makes it worse. Deep space turns milliseconds into minutes. The moon is a little over a light second away. That's a round-trip radio of a few seconds. Mars wanders between about 4 and 24 light minutes one way depending on the orbits, so rovers can't be driven like RC cars. Teams send bundles of commands. Wait, read telemetry, update, and wait again. At the far edge of the planetary zoo, Jupiter is tens of light minutes. Pluto is hours Voyager 1, still talking, sits over 20 light hours distant. Real-time conversation is gone. You exchange letters with patient machines. The same ceiling shapes design inside machines. Fast memory sits close to CPUs, so signals stay short. Chips spread loads across cores because asking one core to do everything would force long, slow trips across silicon. Data centers place services near users. Edge boxes move content outward, so last-mile latency shrinks. Compression buys bandwidth, not latency. Bigger pipes help you send more per second, but they do not make the first byte arrive sooner. Nor do showy stunts beat the limit. A laser spot can race across the moon faster than light, but it's only a moving pattern. No bit rides with it. Metamaterials can make pulse peaks slide strangely, but the earliest detectable change still honors C. Gravitational lensing makes pretty shortcuts in angle, not superluminal tunnels in time, and wormholes belong to math until a lab proves otherwise. The sober comfort is that once you accept latency as physics, systems get saner. You cache, pre-compute, mirror data, send fewer round trips, keep conversations local, design for eventual agreement instead of instant global truth, and set expectations that Mars won't text back quickly. The speed of light is not a nuisance in this story. It's the yardstick that keeps causality straight, sets the creative constraints that make networks robust, and turns the whole planet and the solar system into a map drawn in milliseconds and minutes. Picture a ship that keeps a steady 1G push, so the crew feels Earth gravity the whole way out, flips at the halfway mark, and pushes the other way to brake. That steady shove is called proper acceleration, the acceleration measured by an onboard accelerometer, not by distant observers. And it's the right way to talk about comfort in relativity. Under constant proper acceleration, your path in space-time is a smooth curve. To people back home, your velocity creeps toward light speed but never reaches it, while time on board stretches compared with time at home. There's a tidy tool for this regime called rapidity. Instead of adding ordinary speeds, which can break the limit, rapidities add like plane numbers and map back to safe sublight speeds automatically. The travel plan is simple in outline. Accelerate half the distance, flip, decelerate the rest. The details are brutal because the fuel math goes from hard to unforgiving. The relativistic rocket equation says your mass ratio, wet mass divided by dry mass, grows exponentially with the ratio of the total delta V. You need to your exhaust speed. Chemical exhaust speeds are a few kilometers per second. Fusion might reach tens of thousands. A photon rocket, pure light out the back, would have exhaust at the ultimate limit, c. To get a crude ship to a high fraction of light speed and then stop at the far end, the mass ratio with chemical or even fusion exhaust explodes. Most of the ship would be propellant to push propellant. That's why serious concepts try to leave the power plant at home, laser sails, or mine propellant on the way. Scoops in fiction, though real interstellar gas is too thin. While you push, the world looks different. Starlight in front blue shifts and grows harsh. Behind, it reddens and fades. Dust becomes dangerous grit, and even thin interstellar gas hits like radiation. You also grow a Rindler horizon, a one-way boundary behind you made by your constant acceleration. Signals sent from far enough back after a certain moment will never catch you while you keep pushing. To you, that patch of the universe fades toward a dark edge. This isn't a magic black hole. Stop accelerating and the horizon dissolves, but it shows how C and steady acceleration team up to make cause and effect local. There's an even stranger footnote called the Unruh effect. An ideal detector that accelerates forever would register a faint bath of warm radiation, as if motion through empty space made a thin fog of heat. At 1 g, that temperature is absurdly tiny, far below anything you could measure. So it's a curiosity, not a hazard, but it's a reminder that acceleration and quantum fields interact in subtle ways. Navigation under push is kinder than the fuel budget. 1 g proper acceleration gives you nice human rhythms, artificial gravity, comfortable beds, and a natural flip day in the middle. Time dilation is the real gain. Because your proper time runs shorter than the stay-at-home path, you can, in principle, cross great stretches of the galaxy in a working lifetime as far as you feel it, with centuries passing outside. The cost is paid in energy, shielding, and waste heat. Any high-power ship must dump gigawatts through radiators that will glow like tiny suns, and every kilogram of radiator and shield is another kilogram to push. That's why the first near-relativistic travelers will almost certainly be gram-scale probes surfing light from a huge laser array, not crude craft hauling fuel. The headline never changes. A steady shove bends your path through space-time, so your own clock runs short and distant, clocks race ahead. Fuel math and the light speed fence keep speed sub-c. Horizons appear behind you while you push, and the dream remains bounded by engineering that treats C as a design spec, not a suggestion. The cleanest way to see the speed limit written into matter is to look at the master bookkeeping line that particles obey. E squared equals p squared, c squared, plus m squared, c to the fourth power. You don't need the algebra, only the shapes it allows. If the rest mass m is 0, the equation collapses to E equals pc. Energy is just momentum times the same constant c, which means the only worldlings that make sense are those on the light cone, exactly at the vacuum speed, not a hair slower or faster. That's the photon's life. No rest frame, no idling, always moving at c locally. If m is non-zero, then even with zero momentum, you already carry energy, mc squared. As you add momentum, your speed creeps towards c, but never reaches it, because the extra energy increasingly goes into the m squared c to the fourth part of the ledger, time dilation and momentum, rather than into more speed. This is the modern clean reason the old relativistic mass increases story can be retired. The rest mass stays fixed. The energy and momentum explode as you try to flatten your world line onto the light cone, and the cost curve to touch C goes to infinity. Why are some fields massless in the first place? For the photon, it's symmetry. Electromagnetism has a gauge freedom, roughly a redundancy in how we describe the potentials, that forbids a mass term in the simple theory. Give the photon even a tiny mass, and Coulomb's law would warp. Magnetic fields from Jupiter to your fridge would fall off wrong, and radio waves would attenuate in ways we do not see. Astronomy and lab tests put the photon mass consistent with zero to absurd precision. Gluons, the force carriers inside protons, are massless by the same gauge logic, but we never see free gluons because the strong force confines. Their masslessness sets the rules of the field, even though the field binds quarks into heavy composites. Gravitational waves, ripples of space-time, behave as if their quanta are massless too. LIGO's timing shows their speed matches light to incredible accuracy, which crushes any graviton mass to, if not zero, then unimaginably tiny. Massive particles owe their inertia to a different piece of the standard model, the Higgs field. In plain terms, several fundamental fields would be massless if left alone. Interacting with the Higgs gives them rest energy without breaking the symmetries. We need to keep the equations consistent. Mass from the Higgs is not magic frosting added later. It's that moving those fields through space drags against a background field, and that drag shows up as the mc² in the ledger. Neutrinos complicate the tidy story by being tiny but not zero in mass, which we learned because they change flavor in flight. That small mass means they always move a whisper under C and never at C, and over cosmic baselines we can, in principle, see the difference. None of this opens a loophole to go faster than light by turning off mass. The Higgs isn't a switch you can flip on a whim, it's woven into the vacuum itself. Even if you could somehow strip mass, you wouldn't make a superluminal traveler. You would make a different massless excitation that must live on the light cone. Nor do materials that slow light give shortcuts. They delay light by temporary storage in matter. They don't change the invariant C that ties space to time. The difference between massless and massive shows up in how clocks behave. Massless travelers have zero proper time between emission and absorption. They do not experience a then and now along their path in the way a massive traveler does. Massive travelers trace time-like paths rich with proper time. Their own clocks tick, and the faster they go, the fewer ticks fit between two shared events compared with a twin who rested. Try to bend a massive particle's trajectory at near C, and another cost appears: synchrotron radiation. Circling charges radiate, and the power they dump scales ferociously with their energy, which is why big physics rings grow huge, to soften the bends so you don't bleed away everything you pump in. That, too, is the same geometry pushing back. You can pour in energy, and you can skim closer and closer to the cone, but every method you try hands the bill back through time dilation, momentum growth, and radiation losses. Pull back and the rule set is simple. Massless excitations ride the light cone because the equations allow nothing else. Massive ones live inside the cone and can approach its skin only at infinite cost. The constants and symmetries that pick which fields have mass are part of the vacuum's architecture, not engineering options. The speed of light isn't a number pasted onto the story. It is the slope that both kinds of world lines measure themselves against, the same slope that turns kilograms into joules and makes faster than light not merely hard, but undefined within the grammar of the world. If the speed of light is the hard fence for motion, modern science flips the story and uses that fence as a tool. We define distance by time, and we build time from atoms. The base unit is the second, and its recipe is plain but precise. Take a cloud of cesium atoms, tune microwaves until the atoms flip between two energy levels just right, and count exactly 9,192,631,770 cycles. That count is 1 second. Because every cesium atom is the same everywhere, the second does not depend on a gear, a spring, or the weather. Once you lock the second, the meter falls out. In 1983, we stopped measuring the speed of light, and instead defined the meter as how far light travels in 1 divided by 299,792,458 of a second. That move nailed distance to a constant that nature already enforces. Now, any time you can keep time honestly, you can make a ruler by letting light run. The craft since then has been to make the second steadier. Cesium is good. Optical clocks are better. Instead of counting microwave ticks, they count light waves from atoms like strontium, ytterbium, or an aluminum ion which buzz much faster. Faster ticks give finer marks. The best optical clocks can compare time to parts in a billion. With that sharpness, you see gravity bend time over a few centimeters of height. A clock on a top shelf really does tick a touch faster than a twin on the floor. Labs link such clocks with lasers sent through air or fiber and compare phases to squeeze out the last scraps of noise. Time is then pooled across national labs to make a smooth global average called International Atomic Time. UTC, the civil time on your phone, is that average plus the occasional leap second to keep noon near the sun. GPS runs on its own steady time without leap seconds and broadcasts it from orbit, along with clocked corrections and detailed orbits. Your phone solves for position and its own time error at once, which is why timing lies at the core of navigation. The next step is to move the official second from cesium to one of the optical transitions. That will not make your wristwatch better overnight. It will let us compare clocks across continents more tightly, map the small changes in Earth's gravity by watching how clocks speed up and slow down with height, and test basic physics by hunting for tiny drifts in constants. Building these clocks is a mix of calm and wild. At their heart are quiet atoms trapped by laser light or electric fields. Around them is a forest of stabilized lasers, vacuum chambers, temperature control, and vibration isolation. The goal is simple: keep the atoms still, keep the light pure, count without missing a beat. When two such clocks are carried to mountaintops and cities, and then compared later, they line up within their tiny error bars. When a clock rides a plane, it shows both motion and height effects exactly as relativity says. When an earthquake strains a fiber link, the phase wiggle is visible in the timing data. All of this circles back to light speed. We do not chase c anymore. We use c as the conversion between duration and distance. Fiber links and satellite links move time around the planet. Interferometers measure length by comparing light phases. Chip makers etch features by timing pulses. Radio telescopes spread over continents joined by time tags to act like a single dish as big as the Earth. The constant is the glue. It turns counting into surveying and makes every honest clock a ruler. The future second will click faster and finer, but the frame stays the same. Fix time with atoms, get space from light, and let the hardest speed in the universe be the simplest tool on your bench. When people hear nothing outruns light, the next thought is clever. Don't go through space faster. Bend space so the distance shrinks, like stepping through a door instead of walking the hallway. Two ideas live here. A wormhole is a tunnel whose ends sit far apart in ordinary space but are neighbors in the tunnel. An Alcubierre, Warp bubble squashes space in front of a ship and stretches it behind, so the bubble rides a moving ripple, while the ship inside never breaks the local speed limit. Both sound like cheats that keep relativity happy, because locally, nothing exceeds c. Space-time itself does the moving. The problem is the bill. To hold a wormhole open, you need negative energy, stuff that gravitates the wrong way to stop the tunnel from collapsing. We can make tiny temporary negative energy effects, the Casimir setup with closely spaced plates, but quantum rules put harsh bounds on how much and for how long. Quantum inequalities. The amounts needed to prop open a human-sized throat are wildly beyond anything we can sustain, and any realistic tunnel would be unstable. Stray radiation and tiny disturbances tend to make it pinch shut or explode. Warp bubbles hit the same wall. The original math asked for negative energy with a total magnitude comparable to a planet. Or worse, concentrated in an absurdly thin shell, later tweaks lowered the total, but only by making the shell thinner and nastier, which clashes even harder with quantum limits. Worse, a bubble you can ride is not a bubble you can steer. Inside, light cannot climb forward through the front wall, so you cannot reach out to shape the wave you're surfing. External beacons could, in principle, assemble the bubble around you, but then you need a galaxy-scale engineering project to lay track before every trip. Even if you ignore engineering, consistency bites. A traversable wormhole you can drag around lets you build time machines by moving one mouth and lining clocks up just so. The same goes for certain warp schemes that raises causality problems, loops where effects create their causes. Many physicists expect chronology protection. Quantum back reaction floods the device with radiation or destabilizes it before paradoxes form. Detailed studies find more thorns. A warp bow wave would blue shift ambient photons and particles into lethal radiation at the front, baking whatever the bubble approaches. The bubble's leading edge acts like a horizon. Quantum fields near horizons tend to spawn intense particle baths, a cousin of Hawking radiation. Threatening any craft inside builds stronger shields, and you've added mass and heat you must manage, and you still haven't solved how to start or stop the bubble without spraying destructive shocks across your path. Wormholes come with topological censorship. In sensible, energy-respecting universes, causal curves that try to thread non-trivial tunnels can't get through. Another way of saying the conditions you need violate the energy assumptions. Ordinary matter obeys. None of this proves such shortcuts are mathematically impossible. General relativity's equations admit them as solutions. The point is plainer. In the real world, with quantum fields, noisy radiation, and materials that obey normal energy conditions, every road to a shortcut runs into the same barricades. Vast negative energy you can't accumulate, instabilities you can't tame, horizons you can't control, or paradoxes the universe refuses to allow. Crucially, if a shortcut ever did work, it still wouldn't let you locally go faster than light. It would rearrange the stage so the trip looks shorter from outside. That keeps the core rule intact. Information never outruns light in its own patch of space-time. For now, our best bets for near-relativistic reach stay humble and honest. Light sails pushed by giant lasers, tiny probes that accept long letters home, and patient missions that treat T as a design spec, not a suggestion. In the closing act, we'll gather the lessons into one calm picture. A universe where C is both fence and tool, where limits don't crush discovery, they shape it. We've walked the same bright line from a dozen angles and it never moved. The speed of light isn't just a big number. It's the seam that stitches distance to duration and keeps cause ahead of effect. Hold that seam and the rest falls into place. Moving clocks slow just enough, fast rulers shorten just enough, and no stack of boosts ever breaks the limit. Waves can slide their peaks, patterns can outrun their shadows, entanglement can share correlations. But usable messages still ride the front, and the front never beats. See, gravity doesn't tug light, it bends the stage. Lenses split galaxies, clocks drift with height, colors stretch climbing out of wells, and yet locally the beam is always at full pace. Expansion stretches maps so far things recede faster than light without anyone speeding through their neighborhood. Engineering turns the fence into a tool. GPS trades picoseconds for meters. Fiber and satellites live under latency the way ships live under weather. Optical clocks make rulers from time, and networks stay sane by respecting happens before. Dreaming bigger, the same rules keep us honest. Near-light travel buys time dilation, but pays in energy, shielding, and heat. Warp and wormholes stay math until the universe signs the invoice for negative energy and stability, which it hasn't. Massless things must live on the cone, massive things must live within it. E equals mc squared is the quiet exchange rate that balances the books. If you want one sentence to carry out of this, the speed of light is the world's grammar, limits that protect meaning, a ruler that turns seconds into meters, and a compass that keeps every story causal. With that grammar, you can read the night sky as a record of the past and build machines that work tomorrow. Thanks for spending this calm hour with me. Thank you for watching, and good night.